Hello WindPOWER students, welcome back. We're into our third part of the lecture now about different kinds of weather systems and kind of just introducing some of the key topics about these systems so we can use some of these terms when we're discussing wind and wind energy and wind power production. And now we're talking about hurricanes. And if we wanted to have just a simple introduction to meteorology type definition of a hurricane, we would see that the glossary tells us that a hurricane is a tropical cyclone with winds of at least 74 miles per hour. We'll come back to that word tropical cyclone in just a little bit, but notice that it has to have winds of at least 74 miles per hour. Actually, that is exactly how we decide when to call it a hurricane, is that it has to have had some kind of wind observation of at least 74 miles per hour. You probably know that means that that's a Category 1 hurricane, and then as the winds get stronger and stronger, there's thresholds to call it a Category 2 hurricane or a Category 3 hurricane or whatever. If it's less than 74 miles per hour, a tropical cyclone has a variety of different names depending on how strong it is. You've probably heard of terms like tropical storm or tropical depression, and they all have formal definitions as well that are based on their wind speed. Just to hit for a moment on that word tropical cyclone, notice that this is a tropical cyclone, which is actually very different than a mid-latitude cyclone, the kind that we learned about in part 1 of this lecture. There's actually virtually nothing in common short of them both being areas of low pressure. I've made a kind of a diagram here where the column on the left is for hurricanes and the column on the right is the same features but for mid-latitude cyclones. And one of the main things that's interesting about hurricanes is that they actually have their strongest winds in the boundary layer, quite close to the surface. When you hear that some hurricane came ashore with 120 mile an hour winds, those are the strongest winds. If you went up in the atmosphere, the winds would actually be considerably weaker. In fact, in mid-levels of the troposphere, their winds are quite weak in a hurricane. You often hear about these hurricane hunter aircraft that penetrate hurricanes, and you may think that's very brave and stuff like that, but actually where they're traveling, the storms are hardly all that severe. It would be different if the hurricane hunters were sailing a ship into the hurricane or something like that. That would be a much more difficult and dangerous enterprise. In contrast, a mid-latitude cyclone has its strongest winds up at the level of the jet stream. Mid-latitude cyclones are attached to the mid-latitude jet stream, and that's where the strongest winds are going to be. Hurricanes are typically very symmetric. They occur in an environment where it's about the same temperature all the way around the system. So it isn't like somehow the north side of the system is colder than the south side of the system, or the west side of the hurricane is drier than the east side of the hurricane. Hurricanes are pretty much the same all the way around, and that's completely different than what a mid-latitude cyclone works. In fact, that's part of how a mid-latitude cyclone's processes of getting started, its cyclogenesis of work, is that one side has to be cold and one side has to be warm. You have to have this temperature difference. Yeah, the system has to be asymmetric like that. Another important difference is that the pressure is so different in a hurricane than in a mid-latitude cyclone. They're both low pressure, but hurricanes typically have very low pressure. At the center of a hurricane, a typical low pressure might be something like 950 millibars. A really strong, like record-breaking type hurricane might be more like 880 millibars. Just to give you a sense, if average sea level pressure is about 1,013 millibars, a typical mid-latitude cyclone that might move through Omaha on any given day has a pressure between about 990 and 1,010 millibars. 990, frankly, would be a pretty strong cyclone, a mid-latitude cyclone. The structure of these two types of storms are very different too. That's the last row on this table. Hurricanes have a lot of features that you have heard these names before. The eye of the hurricane, the eye wall of the hurricane, the rain bands of the hurricane. We'll see some examples of all of these. This is all very different in terms of how it works than a mid-latitude cyclone, which has cold fronts and warm fronts and a mid-latitude jet stream and so on. There's actually quite a laundry list of ways in which these two types of storms are different, but it's not necessarily helpful for us to take such a big inventory of all of that. Now, let's talk a little bit about hurricanes and their structure and so on. If I just have this beautiful satellite picture here of a hurricane, what I see is that the hurricane is pretty big. There's no land on here for scale. The actual center of the storm might only be a few tens of kilometers across, but the whole thing and its whole circulation spans hundreds of kilometers, and its whole track might span thousands of kilometers. We describe them as being synoptic in scale. They last, approximately a week on average. That doesn't mean they last a week at any given spot. Hurricanes move, so, any given spot might be only under the storm for a matter of hours or something like that. But the whole thing will have lasted on the order of a week or so. Down at the surface, the winds in a hurricane are rotating around the area of low pressure at the center, and they're rotating counterclockwise, just like around a mid-latitude cyclone. Down there at the surface, and in the boundary layer, those winds are going to be Ekman layer type winds, where they are spiraling in towards the center of the mid-latitude cyclone. The tropical cyclone. The winds are going to be crossing isobars in towards the center. Again, in a more technical class, we'd actually learn that it has to do that, and this is part of how a hurricane does work, and we would make Carnot cycle diagrams of them and all this kind of stuff to show that this is how a hurricane produces mechanical work, and we don't need to worry about that right now. We just are kind of getting a sense of, oh, look, hurricane. We're kind of getting some vocabulary for describing them and so on. You can see that the hurricane is an area of convergence near the surface, and, well, it's got storms and stuff, and storms are associated with rising motion, so it's one of these kinds of features where we have air converging at the surface, rising through the depth of the troposphere, and then spreading out near the tropopause. And that's a pretty good description of what a hurricane does, except a hurricane is different. It has a narrow area of sinking motion right in the middle. Right in the eye of the hurricane, there is actually sinking motion. Again, we're not going to do hurricane dynamics here, where we actually work through the forces acting on all of the different parts of the hurricane and so on. But this is something a little bit weird. Some of the air that rises in the eye wall, the thunderstorms around the eye, does actually sink down in the middle of the hurricane, forming the eye. And so when you look at a hurricane like on a satellite picture or something like that, you can see that most of the time they have an eye, which is this clear area in the center of the hurricane. And that's where there's actually sinking motion going on. Even though it's an area of low pressure at the surface, there's actually sinking motion going on. Tropical cyclones do not work the same way as mid-latitude cyclones. They are a different phenomenon. The eye wall is that circle of thunderstorms that occurs right around the eye. And that is where the strongest winds are happening, the heaviest rain is happening, the highest storm surge. We'll talk about that term on a different day. That is where the worst of the storm is happening, that kind of donut-shaped area around the eye of the storm. If you examine that satellite picture, you can see another thing that's going on, is that there are these sort of pinwheel-shaped bands of clouds that start on the outside of the hurricane and work and kind of spiral in towards the center. Those are called rain bands. And they are, in fact, what produces enormous amounts of precipitation in the hurricane. And they are nothing like fronts. In some ways, they kind of look like a front. I mean, they look like they're a boundary between an air mass like coming... Maybe the hurricane is dragging colder air from the north and pushing warmer air from the south. And no, they're not fronts at all. The weather on either side of these rain bands is the same. Okay, they're both in the same air mass and so on. But, again, we're not talking about mid-latitude cyclone. We're talking about a hurricane here, and this is how its features work. Now, this word hurricane is specifically a word that we use to describe a tropical cyclone when it happens in the Atlantic or in the Eastern Pacific. So like on either side of, say, Central America. That would be a good way to think about it. You've probably heard of typhoons. Typhoons are the same thing. Okay, typhoon is just a different word for the same kind of storm system, except now we're in the Western Pacific. Why do we have a different word for them? Because frankly, until the era of satellite meteorology, we didn't know that these were the same kind of storms. It wasn't until we could look at them from above that we could see, oh, those big things that was causing trouble in the Western Pacific, they're the same thing as what we see in the Atlantic. So we have two different terms, but one of the things I want to draw your attention to, I mean, it's kind of interesting that there's two different terms, but it illuminates an interesting point. Notice that whether we call them a hurricane or a typhoon depends on which ocean they're in, and this tells us something important. There's a connection between hurricanes and oceans. In fact, hurricanes can only form over oceans, and spend practically all of their lives over oceans. Here's a nifty plot that I swiped from someplace, I think off Wikipedia actually, that just shows the tracks of every tropical cyclone over, I forget, a 10-year period or something like that. And what we see here, it might be longer than that, maybe it seems like a lot of hurricanes on there, is that you see all these tracks, and they're mostly at sea. Okay? Hurricanes are principally a phenomenon at sea. Well, of course, we care about them a great deal when they hit land. They actually live practically their entire lives at sea. And they actually, if you kind of zoom in here a little bit, we can actually get a sense from these tracks that they all follow kind of similar paths, where they form in the tropics, and then the trade winds push the hurricanes to the west. Remember, trade winds are easterly winds. They are from the east, and they are surface phenomena. They're the winds near the surface of the earth that are pushing in the tropics from east to west, which is kind of amazing. So these giant killer storms, hurricanes, with these enormous amounts of kinetic energy and so on, are just being pushed around by the trade winds? Yeah. As strong as a hurricane is, it is basically just a blimp. It is a balloon. It's just being pushed by the gentle winds around it. Again, when you learn about things like these hurricane hunter missions where they go with aircraft out to measure a hurricane and so on, you often will see the dramatic part of this on the news where where the hurricane hunter aircraft punched through the center of the hurricane and so on. Actually, they do that very little. Most of the time, what they're doing is flying around the outside of the hurricane, measuring the winds all the way around it, trying to figure out which way the trade winds and so on are steering the system, which is kind of amazing if you think about it. Anyway, it's not going to be our only time that we see an example of some ferocious kind of storm is just being pushed around by the gentle winds around it. I want to draw your attention to a couple of interesting things about these hurricanes on here. I put the equator on this plot just to draw out the fact that, notice, there are no hurricanes at the equator. They don't form at the equator, they don't cross the equator, and there's a good reason for that. Hurricanes are not in geostrophic balance. They're not exactly in Goldberg-Mohn balance. They're not in any of these kinds of, they're not well approximated by any of those kinds of flow, but the kind of flow that is around a hurricane does require the Coriolis force as part of the understanding of the forces that work on air parcels around, in this case, a hurricane. So if you're at the equator, there's no Coriolis force. There's no way to make the winds around a hurricane work. In fact, even within, maybe 5 degrees north and south of the equator, there's no way to make a hurricane work. You need more Coriolis force than that. Now, that being said, notice that the hurricanes are a tropical meteorology phenomenon. I mean, all of these hurricanes are originating at tropical or subtropical, that is to say, slightly outside of the tropics, at tropical or subtropical latitudes, because that's where the warmest waters are. Remember, hurricanes are really intimately tied to what's going on in the ocean, and if I just pull up a typical map of sea surface temperature, now I foolishly cut off, when I got this thing, I cut off the key, but knowing that the yellows and oranges and so on are the warmest water temperatures, you can see where the warmest waters are in the tropics is almost exactly where the hurricanes were. And that's not a coincidence, okay? Hurricanes need high sea surface temperatures. In fact, you basically cannot get a hurricane to form if the water temperature is less than 26.5 degrees Celsius or 80 degrees Fahrenheit. Maybe as much as a half degree below that, you can still get a half degree Celsius below that, you could still get a hurricane, but basically below 26 degrees Celsius, it isn't going to happen. Or about 79 degrees Fahrenheit. That's pretty warm ocean water. How come it takes such warm ocean water to make a hurricane? I mean, why does the water's temperature matter? Well, it's linked very closely to the fundamental challenge a hurricane faces in its life. See, hurricanes produce an astonishing amount of precipitation. When a hurricane is at its full strength, it can be producing several inches of rain per hour. That's really an amazing amount of precipitation, and when you think about it, it's kind of a weird thing. I mean, every drop of water that falls out of the storm was water vapor that the storm converted into liquid water and dropped out as rain. So every drop of rain that falls out of that storm is water vapor that is gone now from the storm. Well, if you're a hurricane and you're producing, 3-4 inches of rain an hour, wow, that's a lot of liquid water. In fact, that's an enormous amount of water vapor. So, in a course of maybe a few hours at that rain rate, you'll use up all the water vapor in the hurricane. Now there'll be no water vapor in the storm to convert into liquid water, and there's no rain, there's no storm or anything anymore. In other words, if the hurricane is dumping this enormous amount of water in the form of precipitation and doing it by converting water vapor into this enormous amount of liquid water, the hurricane also needs to have enormous amounts, it has to have a very good source of water vapor to put more water vapor back in the hurricane that then the hurricane can convert back into precipitation. Okay, that makes some good measure of sense. The hurricane is just a mechanism then for getting water to turn into water vapor, and then the water vapor to get turned back into rain and dumped back to the surface. Well, how do we get all that evaporation from a hurricane? Well, so that we can get all that water vapor into the storm. Well, for one thing, the hurricane's going to have to be over water. Okay, there's no way there's going to be enough evaporation over land to replace all that water vapor that is being converted into rain in the storm. So it's going to have to be over the ocean. And it's part of the reason why the hurricane has to have strong winds. The evaporation rate is partly related to the speed of the wind blowing over the ocean, so the very strong winds of the hurricane are producing enormous amounts of evaporation. So that part I can kind of see, but there's a little detail in there. The rate at which water evaporates depends on the temperature of the water. The warmer the water is, the faster it evaporates. Now, that can be kind of hard to see. I mean, when I have a cup of coffee sitting on the table and I have a glass of water sitting on the table, I don't really notice that the coffee is evaporating more quickly than the water is, than the cup of water is. But that's because I'm impatient and I'm not going to watch it for a very long time, and I'm not blowing a 120 mile an hour wind across the surface of my cup of coffee. I'm not going to keep the coffee all that long. It's not going to have all this difference between the winds. If I were to do that, I would see, if I would blow the wind across the coffee cup at some high speed, like 100, 120 miles an hour, I would see that the warmer the water is, the more evaporation I would be getting. And it turns out with the speeds of winds associated from a hurricane, until you hit about 26.5 degrees Celsius or about 80 degrees Fahrenheit, yes, there's still a lot of evaporation, but it isn't until you hit that amount of that temperature that you're finally getting fast enough evaporation off the surface of the ocean that you're replacing water vapor in the hurricane as fast as you are changing the water vapor back into precipitation and dumping it on the ground. So see, there's sort of a little cycle here. Hurricanes produce all this rain, but that means you gotta have a lot of condensation in the clouds, changing water vapor back into liquid water. If you don't want your storm to run out of water vapor and be done, you're going to need a lot of evaporation. And the strong winds around the hurricane at the surface will be a big part of the story, but you're going to need to have the warmest possible waters at the surface for the winds to blow across, produce a lot of evaporation, and carry that water vapor into the center of the hurricane, into the eye wall and so on, to be converted back into precipitation. Hurricanes have these strong winds over a relatively large area. In fact, in terms of the total kinetic energy, it's often said that hurricanes are the strongest storms on Earth. I mean, a tornado is much stronger winds. Tornadoes have winds of like 300 miles an hour. A hurricane has winds of like 120 miles per hour. But a hurricane is many times larger and lasts much, much longer. So, gosh, it would be awesome if we could find some way to harness that. In fact, I even stole this nifty picture here, illustration of a wind turbine at sea in a hurricane or whatever, from a website that was advocating finding a way to deploy wind turbines to capture the energy of a hurricane, and you can just forget that. That is not going to be happening anytime soon. It would be very cool, but first off, the engineering challenge of making a wind turbine that could survive hurricane force winds is just, I mean, how should I put it? If we have technology to do that, we'd be better, we'd have better ways to use the technology, like, make more efficient turbines for on land, or make cheaper turbines so we could have more of them on land. It would not be a very efficient way to do it, to make a turbine that can withstand a 120 mile an hour wind at sea in a hostile environment. Secondly, the width of the hurricane is on the order of a few hundred kilometers for the whole system. The eye wall itself is only maybe a few tens of kilometers across. And they don't happen all the time. The hurricanes aren't there, 365 days a year. This would just not be a very efficient plan. It's kind of a cool thought process problem. In fact, later in the semester, we might, for one of the discussions, work on that a little bit more. But it is not the most not the best use of resources to be thinking in terms of how we can harness the power of the wind of a hurricane. Now, we might think, well, gosh, what about if a hurricane just happened to hit your wind turbines that were on land? Well, first off, if they are, if you have wind turbines right near the shore or something like that, when the hurricane comes ashore, that could be more of a safety issue. You'd have to worry about shutting the turbine down and so on during the storm. And actually, once the storm moves inland, the winds decrease surprisingly rapidly. This happens to be just a map of the peak wind gusts during the landfall of Hurricane Sandy a few years ago. Even when you're just a few miles inland on the counties right by the shore, the winds are already dropping off dramatically, and you're not seeing particularly high winds anymore. It's just not really a practical thing to think that in any way you could exploit the winds of a hurricane. Despite the fact that that sounds like a really cool idea, it just doesn't work that way. Alright, man, take my tropical meteorology class and you'll learn a whole lot more about hurricanes, but that'll at least give us some basic ideas about them as we come across them other times this semester. Let's answer a couple quick questions about hurricanes before we move on to the final part of this lecture. In question 11, unlike a mid-latitude cyclone, a tropical cyclone, that is a hurricane, is an area of high pressure. True or false? Alright, make your choice for those two options and get a little feedback before you move on to question 12.